You know, every single time you open a web browser, check your morning email, stream a video, or just download a file, you are interacting with what computer scientists call the application layer. It's literally the topmost layer of our internet architecture, the one that we, as end users, actually see and touch every day. And in this explainer, we're taking a really fascinating tour right under the hood to see exactly how these everyday marvels are actually built. We're going to look at the hidden blueprints, the virtual post offices, and the decentralized revolutions that make the modern internet function.
All right, let's dive right in. On our agenda today, first up, the foundational client-server blueprint. Second, DNS as the internet's phonebook. Third, the World Wide Web. Fourth, email routing behind the scenes. And finally, the peer-to-peer revolution.
Starting with Section 1, the client-server blueprint, the foundation of network apps.
To really grasp how our network apps work, we've got to set the stage with the absolute dominant architectural model of the internet. For decades, the vast majority of the web has relied on a very specific, pretty rigid division of labor between two distinct types of computers. You've got clients and you've got servers. A client is typically that simpler machine sitting on your desk or in your pocket, like your laptop or smartphone. It runs a client process, say a web browser, which sends a message over the network asking for data. On the flip side, you have the server. Servers are usually these incredibly powerful, centrally housed machines maintained by system admins. They just sit there, constantly listening and waiting for incoming connections. When a server gets a request, it does all the heavy lifting, looking up databases, fetching files, and then fires a reply back across the network to the client. It's a setup that lets one single server handle hundreds or even thousands of clients all at once.
But hang on a second. A single remote computer might be running a web server, a video server, and a mail server all at the exact same time. So how does your client software know which one it's supposed to talk to? Well, this is where the concept of a port becomes absolutely crucial. Think of it like a telephone system. If an IP address is a company's main phone number, the port is the specific extension for the exact department you want to reach. Port 80, for instance, is the standard extension for a web server, while port 25 is typically for an email server. It's this brilliant logical endpoint that makes sure your web browser doesn't accidentally start chatting with a remote machine's email software.
Moving right along to Section 2, DNS, the Internet's phonebook.
As we transition to the next room in our tour, we hit a really fundamental translation problem. See, we humans are great at remembering words, like the names of our favorite websites. But computers, they literally only speak in numbers, specifically IP addresses. So ask yourself, how does your computer actually know where Google.com is in the physical world? Because just typing google.com into a browser doesn't inherently tell your machine how to route packets across the globe. We need a translator.
And that brings us to DNS, the domain name system. It's essentially a massive hierarchical distributed database. The second you type a URL, your computer's resolver software springs into action. First, it taps your local name server on the shoulder and asks for the IP address. If the local server is like, I don't know, the query moves up the chain to a root server, which then points it to a top-level domain server like the big boss in charge of all the .com addresses. This iterative, step-by-step hunt keeps going down the hierarchy until a server finally responds with what's called an A record, handing over the exact IP address. Once your machine has that number, DNS's job is done, and your browser can actually start the connection.
All right, Section 3, the World Wide Web, HTTP, and browsers.
With our phonebook translation out of the way, let's look at the most visited destination on the internet. Believe it or not, the web was originally developed way back in 1989 at the CERN High Energy Physics Lab, basically just as a way for scientists to share and edit hypertext documents. Today, it's the absolute dominant application layer protocol, and the system that makes it all possible is HTTP, or Hypertext Transfer Protocol. It's actually a surprisingly simple, elegant request and response cycle that runs over a TCP connection. Your browser sends an HTTP request, using a command like GET to ask for a specific page. The server gets this, grabs the HTML document from its database, and shoots back an HTTP response containing that file. Because HTTP is so standardized, it seamlessly lets you jump from a server down the street to one halfway across the globe, and you don't even notice the difference.
Let's shift gears to Section 4, email, and what goes on behind the scenes at the virtual post office.
Email actually predates the World Wide Web, and it operates a lot like our physical postal system, using a totally different set of protocols. When you compose a message and smash that send button, your email software, which is known as a mail user agent, talks to a mail transfer agent using a protocol called SMTP, or Simple Mail Transfer Protocol. SMTP is essentially the workhorse for outbound mail. It pushes your message from your local machine to your outbound server and then routes it across the internet, relaying it from server to server until it finally hits the recipient's delivery system.
But how do you actually get your mail out of that final destination server? That's where two competing retrieval protocols come into play. You've got POP3, which is kind of old school. It simply downloads your emails to your local computer and then deletes them from the server entirely. That's super easy on the server, but it's pretty terrible for you if you want to read your mail on both your phone and your laptop. IMAP 4, on the other hand, is built for how we work today. With IMAP 4, your emails are stored, synced, and manipulated directly on the remote server itself. So when you flag a message or create a folder on your phone, boom, that change is instantly reflected everywhere else.
And that brings us to our final stop, Section 5, the peer-to-peer revolution, where we basically throw out the blueprint. Okay, major plot twist time. We've spent this entire explainer talking about the client-server model. But right around the late 1990s, things changed. As home computers got way more powerful and always-on broadband became the norm, people realized something huge. Our personal machines didn't just have to be dumb clients anymore. They could be servers, too. Enter the peer-to-peer, or P2P model. This completely abandons that centralized setup. Instead of dedicated roles for requesting and serving, P2P is fiercely decentralized. Every single node in the network, called a peer, acts as both a client and a server at the exact same time. You're sharing your own bandwidth and storage, talking directly with other users without ever needing a middleman server. It totally eliminates central bottlenecks and single points of failure. The most wildly successful example of this? BitTorrent, created by Bram Cohen back in 2001. Instead of downloading one massive file from a single server, BitTorrent chops the file up into tiny, fixed-sized pieces. A central server known as a tracker helps coordinate this swarm of peers, basically pointing you to other users who have the pieces you're looking for. The peers who have the whole file and stay online just to share it, those are called seeders. But here is the absolute genius of BitTorrent, the tit-for-tat mechanism. In the early days of P2P, people would download what they wanted and just immediately bounce, total free riders. BitTorrent actually forces you to upload data to others if you want to keep your own download speeds high. It literally builds an economic incentive directly into the network protocol.
As we wrap up this architectural tour, it really is incredible to see how the application layer has evolved. From these strict, centralized mainframes all the way to dynamic, decentralized swarms of millions of personal computers. Which leaves us with a pretty massive question to chew on. If the line between who is a server and who is a peer keeps blurring as our devices get smarter and faster, what is the future architecture of the internet actually going to look like? Are centralized servers eventually going to disappear entirely? Thank you so much for joining me on this explainer today. I really hope this sparked your curiosity and that you're leaving hungry to explore even more about the digital world that is constantly running right beneath our fingertips.